Maybe if you can share your screen, that would be great. So, welcome everyone. I'm pleased to see such a good turnout. And it's a real pleasure today to introduce Mohamed Adel Gabry. And he is a postdoctoral fellow at the University of Houston. But on top of that, he's got about a decade of hands-on experience as a subsurface petroleum engineer. And his background spans both conventional and unconventional reservoir development. And his specialization is in hydraulic fracturing, acidizing, well completions, and production optimization. Now, recently, he's been working on advancing signal processing in upstream operations and enabling the integration of machine learning and data-driven technologies. So consequently, his research emphasizes cutting-edge fracture diagnostics, which we'll hear about today, I think, intelligent well optimization, and adaptive reservoir management. So as I said, it's a great pleasure to introduce Mohamed. Mohamed, it's all yours.
Yeah, thanks, Dr. Ken, for this introduction, and thanks for this opportunity. Today, we'll talk about hydraulic fracturing characterization using continuous Fourier transform for treating pressure, and introduce another calibration for this technology using distributed fiber optics data. Our presentation today will introduce the motivation behind this work, to introduce this technology, and why we introduce this technology, and discuss briefly the system of thinking in oil field operation or hydraulic fracturing operation as a signal and system analysis, and introduce one type of Weber transform, which is continuous Weber transform, and the technique specialized for dynamic fracture propagation characterization, which is a normalized continuous Weber transform scalogram, and introduce the calibration using microseismic events and the calibration using distributed fiber optic sensing. The data that we used to calibrate our technology is from Marcellus Shale Energy and the Environment Laboratory, and discuss the three cases that we selected randomly to calibrate our technology using distributed fiber optic sensing to get some conclusions. Our motivation behind this technology that we need to uh, upscale our high technology. We record microseismic events for small percentage of our hydraulic fracturing job. We record record distributed fiber optics sensing in small traces, is in small percentage of our hydraulic fracturing jobs. But the actual fact is treating pressure is the only signal recorded in each hydraulic fracturing job, and high-tech diagnostics, due to its cost, it's a small percentage of these fracture stages. So we need to relate all high-tech technologies to treating pressure to give opportunity for the machine learning to upscale this technology. As you know, the machine learning workflow starts with standardization. So we need a standard methodology for our analysis, then automation, then integrate all technologies and give it opportunity for upscaling to improve scalability, and keep monitoring for continuous improvement. So we need generic solution for our hydraulic fracturing operation or oil field operation. So as we know, we can consider any parameter that we record during our operation as a signal. What is a signal? Simply is a physical quantity that conveys information over independent variable. This variable can be time in hydraulic fracturing, can be depth in drilling application, can be long-term time for interwell connectivity. Any signal that has information that over independent variable can be considered as a signal, and our oil fields or our operation follow these signals. So we need to transform our to introduce this generic solution. We need to transform our methodology of thinking into a signal system analysis. What is the system? Is a transformation that map input signal to output signal. For example, in hydraulic fracturing operation, we pump fluid with viscosity and density. We pump propellant. We pump with a specific pumping rate, and this inputs interact with the system, which is reservoir rock properties, which has permeability, has porosity, has natural fracture intensity, and has a heterogeneity. It's complex process. Then deliver output signal, which is the treating pressure, or in high tech cases, fiber optics or microseismic events, and all this as output of our system. So our technology cons- tries to introduce a generic solution for this output signal to understand the system complexity. So one of the techniques that provide these generic solutions is the wavelet transform. What is the wavelet transform? Wavelet transform is a flexible mathematical microscope for our signal using a short wavy signal, which consider the wavelet. So it's a mathematical convolution between a short wavy signal called wavelet and our signal, and in our case today is the treating pressure. This technology can be applied on any signal, uh, which is data versus time or data versus depth or any data versus independent variable. This mathematical convolution can be done continuously over a range of scales and translations, and can be done on specific locations, which is discrete Wavelet transform. This continuous Wavelet transform provide a magnified version of the data embedded in our signal. This convolution can be done through two main processes. The first process is scaling, which is the compression or stretch for this short wavy signal, and translation by moving this wavelet over the signal to magnify its content. In our technology, we use the standard and the old wavelet used long time ago, which is complex Morley wavelet. We selected complex Morley wavelet to capture all the details embedded in this signal, because the real wavelets has some limitation because some limitation in capturing some details embedded in this signal. The complex Morley wavelet available for all in free in open source Python libraries. It's combination of 3D Gaussian with complex sinusoid wave. It can magnify the treating pressure, and by this convolution. So using continuous Fourier transform, we can extract local time domain and frequency domain information at the same time. So we have flexible mathematical microscope. This flexible mathematical microscope can be real, can be complex, can be stretched, can be compressed. So we have a flexible tool to play with to deal with our signals, and our signal today is the treating pressure during pumping hydraulic fracturing job. It's available in open source Python libraries, can be done through simple Python script. So it's practical and widely used in medical applications and engineering applications. One of the techniques using continuous Fourier transform is to magnify the signal by converting any signal to signal energy scalogram. What's the signal energy scalogram? It's a magnified version of the signal that show the details of this signal. How to construct it? Simply by conduct continuous Fourier transform over a range of scale and translation. So for example, let's start with a specific location and a specific scale, which is represent the stretch or compression of this signal. Then get the coefficient, then change the location along this signal to get the coefficient at this scale. Then stretch it and repeat the process again to get the coefficient over this scale. So we can get with the scale and time the magnified version for this signal. But we can convert it to for better visualization, for better interpretation, to a signal energy. Signal energy is a square of the coefficient, so we can get better version for magnified signal that we analyze using signal energy scalogram. This is so 1D signal converted to a signal energy scalogram that has all the data, the coarse features that take longer time and longer time and lower frequency is a coarse can be shown in higher scale, the coarse features, and the fine features which has higher frequency and lower time is in fine features. So we can magnify the details embedded in this signal, or even both the coarse features that take longer time and short features that take shorter time. So what this technology can introduce in dynamic fracture event detection to monitor our hydraulic fracturing job. We get the hydraulic fracturing data, the heating pressure, the signal that the output signal that we measure in all hydraulic fracturing job. If we have, it's better to be done for the bottom hole, calculated bottom hole pressure to remove the friction effects at perforation. So we advise to apply this technique to the calculated bottom hole pressure. And if you have a bottom hole gauges, it's better to remove all the effect of the fluid changes and the frictions in tubing. It can convert the heating pressure to a magnified version of this technology, or the magnified version of this heating pressure. This magnification introduced by continuous wavelet transform. When we apply this technology over hundreds of jobs, we found that due to changes in scale, we cannot compare uh, we cannot compare jobs, hydraulic fracturing jobs to each other. So we introduced a new technique called normalized continuous wavelet transform scalogram. By normalizing the signal energy scalogram to a normalized version, this normalized version can enhance the interpretation, and it can help us to classify the fracture propagation events. So we detect how the target of this normalization. We need to know when exactly the fracture propagate in length and the fracture propagate in height, and how if this fracture propagation with a good width, or it's limited width, and it can cause a problem in bombing, and that's the main target for creating the normalized continuous wavelet transform scalogram. This normalized continuous wavelet transform scalogram can be done real time. Just update the signal so it can be implemented in the frag van. Update the signal, then within few seconds you can update the scalogram so you can monitor your frag job within during hydraulic fracturing, can be done real time. And this normalized continuous wavelet this scalogram can show how this fracture propagates. How to read it? When you read the scalogram, you consider two main. You consider a struggle between two features: fracture propagation in length, lateral fracture propagation, and the domination of of leak off or interaction with natural fractures or the leak off that that steal the power of the hydraulic fracturing fluid. So this struggle can be understood from when you read the scalogram from the start of job till the end of job. So we read it over time, and with the value of the energy or the value of normalized CWT scalogram coefficient, we can understand it's propagating in length, or it has some limitation in width, or intersect natural fractures. For example, uh, 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 if the value of the normalized CWT scalogram is between 0 and 0.25, we have limited fracture width propagation. So we can see flames, but this flames is mainly dominated by this region of the color, with between 0 and 0.25 for the normalized CWT scalogram coefficient. If this fracture flames increase with time and became dominant with time, at this time period, so we can infer that fracture length growth. And if there is high leak of zone or intersection of natural fracture or fracture propagation in height, we can see it as a domination of high energy in the normalized CWT scalogram. So that's the area of interaction with natural fractures or high leak of zone, and then fracture try to propagate against this source of leak off. So the fracture flames increase again at this time period. Then, as a struggle, as a complex process, as a struggle between two main features, we can get the results magnified in the normalized CWT scalogram. To calibrate this technology, we did a lot of simulation to calibrate to mark each signature on the scalogram. But the best calibration is to calibrate using independent physical measurement, which is the microseismic events. We compare between the scalogram and how the microseismic events propagate in X, Y, and Z relative to the perforation of this fracture stage. We can, by comparison with time, we can find that we also compare this technology to old technique developed by Dr. Solomon and his group, which is moving reference points. Moving reference point technique can also get the fracture events developed, the fracture events to understand how the fracture propagates its length, or its high leak off zone, or propagation, normal fracture propagation, or screen out. It's developed 2013. So we compared by this technology and compared with the microseismic events, we can get that with fracture propagation in length marked by the microseismic events, it's shown increase in flames in hydraulic on the scalogram, and the fracture propagation in height, which is the increase in Z direction of the microseismic events, is happen at the same time of increase of high energy coefficient dominated time. And this is the large scale calibration. We apply this calibration on two different frag data sets on two different locations, and it showed agreement showed the same conclusion from hydraulic based on our interpretation. Another case for microseismic events calibration, we can see that the fracture propagation in height at 4, 5, and 6 is marked on the scalogram. The fracture propagation in length, the increase in dx and dy is linked to at the same time to the increase of flames of hydraulic fracturing jobs. Also, when the fracture flames became more bluish, and it takes lower values for normalized CWT scalogram, so this area is related to low bumping rate and at the start of the job, and the increase of propant, so the width is limited with the propant concentration at this time. So it's can be seen also in on the scalogram for hydraulic fracturing jobs. So this is the largest scale calibration for our technology, and we need to introduce another technology to calibrate our technology on a small scale to see the details of the hydraulic fracturing propagation. So we went to the technology of distributed fiber optic sensing, which is based on it use laser pulses to travel along optical fiber to detect strain, temperature, vibration. There are three types of light scattering. Rayleigh, which is sensitive to strain and temperature, its highest amplitude, and that's what we use today. Beryllium, strain and for strain and temperature, used for distributed strain sensing, and Raman, mostly used for temperature sensing. And we use the backscattered signal to tell what happened along this fiber. How the fracture propagation seen on this fiber by observing the strain rate, with time and depth. So we can by stretching, which represent the stretching on the fiber optics, represent fracture extension, and the compression on fiber optics represent stretch shadowing. So it's not easy in real field case, because our system in subsurface fracture propagation is complex, but we can get frac hits or growth or closure from this strain rate on distributed fiber optic sensing. What we for distributed fiber optic sensing data acquisition or the acoustic signal, we measure the acoustic signal on the distributed fiber optic sensing, and that's really proportional to strain rate. So, and that represent the deformation frequency in the rock. So if this frequency increase, that means we intersect a natural fracture or activate or which is fracture opening or mechanical deformation or turbulence in flow or stress wave interaction near the fiber. The vertical fracture growth, we cannot observe it in horizontal fiber, but can be inferred from the acoustic strain rate better. The set that we use to calibrate our technology is from Marcellus Shale Energy and Environmental Laboratory, MSEEL. They have set a bogus bad well. It's consists of six horizontal wells with laterals over more than 10,000 feet, aligned with minimum horizontal stress. So the fracture propagation in length is optimum transverse fracturing, typical to shale stimulation. And bogus 5 has acoustic data for distributed fiber optic sensing, which available for validation and for research. To compare between different fracture stages for bogus 5, we fixed the range to be between 0 and 1000 hertz. There's all the recorded frequencies are available, but to compare between different stages, we fixed the range to between 0 and 1000 hertz to compare the signature of each stage to compare between each other. The first stage that we choose randomly is the stage 41 in bogus 5. When we get the treating pressure of the stage 41, then apply the normalized CWT scalogram, then compare it as a with time to compare it with the signature of on acoustic signal. Based on this comparison, we can notice that at the start of the job, on the scale between 0 and 1000, we cannot see significant strain rate or acoustic signal on the fiber optics. That's related to dominance of the high energy on normalized CWT scalogram. So our fracture propagation is not significant yet, but at this time at FN2, it starts to dominate the time of the job, and that's where and that's when we get a signature on on the signal of distributed fiber optics acoustic signal, and starts to dominate. Then at event 3, it's again the red areas or the high energy on the scalogram starts to dominate at this time, and that frac propagation and the value of acoustic signals start to diminish and with time, and again, and that's compared, and that's related to the dominance of high energy on the normalized CWT scalogram at the end of the job. We can notice that increase in on increase over the scale, the of high energy on normalized CWT scalogram, and that's related to opening a new fracture at this cluster. So there is to get more intuition of how to read it compared to distributed fiber optics acoustic signal. We can that's the video for the comparison to get how we can read it, the scalogram compared to the fiber optics. The first part, there is no fracture width, enough fracture width to be seen on the fiber optics on frequency between 0 and 1000, and then fracture propagation increase, then start to diminish, and this is a high increase, high dominance over the scales or for the high energy, which represent a new fracture opening or increase in the acoustic at specific cluster. The normalized CWT scalogram, because we use only one treating pressure signal, it can get overall fracture propagation over all the clusters, not specifically per each cluster, to get the final fracture propagation mode. Another fracture stage, compared to the scalogram of previous stage, we can see localized increase in high energy at shorter time. So we expect from only the scalogram there is spots of high energy or high strain rate or high deformation rate at specific times. So that's what exactly the distributed fiber optic sensing data acoustic data showed. It's not higher width, higher acoustic, then diminish. No, it's localized in time. So again, with when we compare the scalogram with distributed fiber optic sensing, at start of the job, not yet fracture propagation starts to propagate. Then when the flame increase on the scalogram, we can see higher acoustic signal, which is represent fracture propagation or start of deformation in this during this time. And again, when there is interaction with natural fracture or opening a fracture, we can see it as a high energy over all scales at this time. At 5 and 6, 4, we have fracture propagation in length, but with same value of the frequency. So that's why we get flames of fractional propagation on the scalogram. And again, at the end of job, there is a increase in the acoustics in this in increase in acoustics in on the fiber optics, which higher steady rate at the end of job. That's also can be seen at event 7, which is present high energy dominance at the during this time period. And this is the video again, compare between the signature that we see on the scalogram and what we expect, or what the distributed fiber optic sensing acoustic data measure in downhole. So we get this information based on free data, which is the TT pressure, no cost added to the job to get this fracture event detection. And this can be done real time, can be done through practical Python scripts. It took no time with the current computational power. Another stage that we used to validate our technology is stage 4 in bogus 5. We can notice from the data acquisition system, it's higher in the range between 0 to 1000. So we expect from, compared to the other stages, it's more generally, it's more dominance of a high energy. So that's what we got when we applied this scalogram. Also, here start to when you start this job, we still within to get deformation of the rock. Then at even 2 start see some deformation. Then as we discussed, it's a struggle between fracture propagation and length, and striking striking high leak of interaction or natural fracture starts to propagate or re- struggle with the fracture propagation in length. And that's what we got specifically when we compare between the scalogram and the acoustic data for the fiber optics. Here's also the video that represent what the comparison between the scalogram, because it shows the fracture propagation in during the hydraulic fracturing job, and how it perform downhole in fiber optic sensing. And that's we can get the fracture propagation events by this comparison. So our technology use the teething pressure to introduce the normalized CWT scalogram. We can in real time detect the fracture events by getting by detecting the lateral fracture growth when there is increase in the green flames, or for the values of normalized CWT scalogram energies between 0.4 and 0.6, height growth or leak of zone, or over all scales shows 0.5, 0.8 to 0.95. If this fracture growth is limited in width, we can the fracture flames will show as a more blue flames between 0.5 0.25. We validated these techniques on distributed fiber optics acoustic data, and using and also previously for against microseismic events development with time on Marcellus Shale. And also we applied this technique on middle Bakken formation, and it worked perfectly, because it provide a complex complex features that can represent the complex fracture propagation downhole. We use only TT pressure recorded in all jobs. So once you train a machine learning model for microseismic with this with this scalogram, with this magnified treating pressure, we can let the machine learning to sensitize fiber optics or sensitize microseismic events based on your treating pressure to be used to be upscaled for all your basin. No need for any downhole sensor or microseismic array. It's just we need the treating pressure to get this technology, and we introduce interpretable high resolution time frequency diagnostics. It can be done over all hydraulic fracturing jobs, can open the door for machine learning, for upscaling, and to predict the high tech technologies for all hydraulic fracturing jobs. This can be done real time, so it's not like Nolte-Smith's technique to compare it to the start of the fracture propagation. It can be done simply, no high computational cost. It's done over simple Python library, open source. It can be done to real-time decision and post-job analysis. Also, it can, if we understand how the fracture propagates and how the stages and is performed and understand how the fracture propagates in real field, we can enhance our hydraulic fracturing design and the stage efficiency, and it reduces significantly diagnostics cost with getting same insights. So at the end, I would like to introduce, it's not just for hydraulic fracturing, it's Wavelet Transform is a new lens for the complexity. Our subsurface formations are complex, and we do as a hydraulic fracturing complex process. So it's we need always to get more and more and more data to calibrate our insights. This is new insights by our technology, and we need to get more and more data by the academia industry collaboration. At the end, for any question, you can contact us, FracWave Research Group, led by Professor Solomon. We have three main technologies. We are working on Wavelet Transform, along with amazing technology with plasma pulse stimulation, which has a great potential for geothermal stimulation, and we work on enhanced geothermal system to develop new technology for the completion of enhanced geothermal systems. And thank you.
Thank you, Mohamed. I agree with Syed Farouk Ali's comment that this was an excellent talk. We have one question, and we'll go to Zeno's question. I don't know whether you can see it, so I'll read it. For normalized CWT, don't you need max and min signal magnitudes during the treatment? How do you manage that for real-time monitoring? And do you have defaults and update?
Because we monitor it with time, so the code itself gets the minimum and maximum over the history. So for real-time application, so we basically measure the trend of or the changes in the treating pressure over the previous signature. So it's automatically over the recorded previous treating pressures. We actually didn't. We need to collaborate with a surface company, a hydraulic fracture company, to apply it to see the efficiency. But from calculation point of view, it can be done real time with no time, so it didn't take longer time in computation that can be obstacle for real time application. So each hydraulic fracture job has its own minimum and maximum, but we mark the fracture propagation signature based on the minimum and maximum for the previous treating pressure points.
So we were joking before the talk that Ali Danashi and Sid Green would have questions. And so I'm going to ask Ali Danashi and Sid Green if they have any questions or observations. Sid raised his hand.
Very nice and very interesting. Trying to harvest additional understanding from the pressure that we have is very interesting, very worthwhile. I'm sure you've thought about this, but you're measuring, you're looking at the stress waves, stress waves in the frac fluid, which result from the pumping and the how the fracture occurs. But what about the pumping? I mean, does the pump itself change this, change these stress waves? I'm sure you've thought of that.
When I think the anomaly done by the frag pump itself can be excluded from the scalogram. So if we know exactly there is anomaly or high frequency events shown on the scalogram, we can simply remove this range of the frequency to get the analysis for the rest of the rest of frequencies. That's the main power for the continuous Fourier transform. I can continuous Fourier transform. We don't get specific range of scale to do our analysis. We magnify it. If we have specific features that related to pump or any surface equipment or non-frac propagation events, we can remove it and do the analysis over the rest of the scales. So it's a magnification. If we have any doubtful data or events, we can remove it and infer to the rest of events to understand how the fracture propagates.
Anyone else? Well, then maybe I'll just ask one. Oh, okay. Well, Yvonne has a question. Could you please elaborate on the kind of pressure signal resolution that you need to run your analysis with?
One of the main advantages of continuous Fourier transform, even the non-uniform sampling rate doesn't matter for the continuous Fourier transform, but all this analysis is done on the normal sampling rate that we deal with in hydraulic fracturing, which is 1 reading per second. So that's the standard in the industry, and that's what we get and what we use in our technology. So no need even for high tech pressure sensors to do this analysis.
No other questions, then I'll ask one. So Mohamed, have you been able to try this on data sets where things like plug bypass or screen out have occurred? Are there situations, as you implied, where a Nolte-Smith analysis isn't enough to diagnose an impending screen out?
Yeah, for the screen out specifically, as you know, Nolte-Smith technique has some limitation because it relate all the fracture propagation to the first point, which is the closure stress. So it doesn't change with the change of the closure stress when the fracture propagation cover higher larger area of the formation. So and we need to know the exact number of the closure stress to get the Nolte-Smith technique accurately. Our technique get the fracture events locally with time. So we based on we didn't actually get data for blood by bus and to calibrate our technology. So we need more collaboration to test this scalogram. But the screen out itself can be seen as the red flag for screen out can be seen as a minimum the width limitation. For example, this job was about to screen out because we have limitation in width, and that made the fracture propagation flame more yellow. So we have higher lower energy on the flames. So the flame itself, which represent fracture propagation in length, is limited in width, and possibly we have a screen out that's related at the end of the job with propant. It can be inferred as a uh, uh, red flag for propant screen out. But that's what we got from one or two jobs when using scalogram. But we need more and more data and more collaboration to understand how the fracture propagates on the scalogram.
Indeed, indeed, lots of possibilities. And Syed is asking, you're using fiber optics only for validation of CWT?
Yeah, we use CWT use only the 3T pressure, and we calibrate it with independent physical measurement, which is the fiber optics.
Okay. Anyone else have any questions? Well, if not, Mohamed, I want to thank you for a great talk. It's really fascinating, and I think it's important to see, as Sid pointed out, people teasing additional information out of pressure data. And so this is fantastic, and thank you so much. And thanks everyone for attending.
Thank you so much for this opportunity.
Good job, Mohamed. Good job. Enjoyed it.
Thank you so much.
You got a lot of positive comments.
Yeah, thank you
Yeah,
so
very
much.
nice stuff.
And actually, in next ATCE, we'll introduce this technology for forge data for AGS.
Oh, I was going to ask. Okay. Yeah, I'd like to see that.
Yeah, all these scalograms for 16A and 16B
Oh, that's fantastic.
is
Yeah,
published
that's
in next in ATCE, in geothermal
okay.
session.
So I have to wait till October.
Yeah.
Okay, okay.
Thank you so much.
Well, very good.
Good
And
job. Thank you, Gabry.
Thank you, Professor. Thank you, Professor Farouk. Thank you so much.